Hello ladies and gentlemen, and welcome back to the 9th laboratory session, which is accompanied with the 12th lecture for GGS 300. And this week in the laboratory session we're going to basically be going over those inferential spatial statistics methods which we covered already within this lecture, which I previously gave. But we're going to be basically carrying out a few processing tasks within ArcGIS, okay, within ArcMap. So hopefully you've actually got a version of that. So I actually have a version on my own machine, but you can access a version of ArcGIS Pro from the GGS laboratory, which all of you should have remote access to, and you should be able to spin up a copy of that remotely using Citrix if you don't have a version on your own machine, and that should enable you to basically get working with the content that we're going to go over here. So hopefully you're going to be able to go into Blackboard and basically get this Lab 9 data that I've got here on my desktop, and I'm just going to open it very quickly. Okay, so I'm just unzipping, extracting all of that data into this one particular place. And you'll see when you get in here that we've basically got some nesting data here, we've got some neighborhood data, and we've got this county data, okay? Within the Lab 9 session there's also going to be a set of directions which I've got here, which I'm just going to open. Okay, so this basically gives us the directions for what we're going to cover within the session. We're actually going to start by focusing on nearest neighbor analysis. Okay, so if we go into the lecture notes, I can just briefly remind you of what we covered within the session. So this is basically how we analyze point patterns, and we're actually able to statistically assess whether we have point patterns that are basically random processes or not. Okay, and basically we've been over these kind of more theoretical requirements, so the assumptions in order for us to use these techniques, and then we're able to produce this ZN test statistic if we're able to basically get these constituent components of this equation and produce this single output here. So look, what I'm going to do is I'm going to start with this bird nest data, okay, that we've got for Travis County, Texas. The question is, well, are the actual nests that we've got placed randomly in a neighborhood or not? Okay, so what we need to do is we need to go to our data, which we've got here. And we basically need to go to the nest data, which is here. So remember that a shapefile usually has about 5 to 6 different components. And what you want here, I'm just going to drag the shapefile in and drop it where we want it. Obviously, that's the single file that we actually access, but these are all the other files that support that data. Okay, so you've got an XML document, SHX file, so on and so forth. So let me just zoom into the data that we've just got. Here we go. So we've got a bunch of birds' nests that we would like to analyze. Okay, so you can have a look at the actual data points that we've got. Now, obviously, the question here is determining whether this is basically a random allocation of birds' nests or whether they're actually clustered. Okay, so our hypothesis is going to be that in the case of the null hypothesis, the NND bar and the NND R bar values here are basically the same. Okay, so that's the observed mean of the nearest neighbor distance and the random mean of the nearest neighbor distance. Okay, so essentially what we're going to do is we're going to go into the spatial statistics toolbox. So this basically means that you don't have to manually carry out these tasks. Okay, so I'm sure you'll be glad about that. So today we're just going to click through from the spatial statistics toolbox into analyzing patterns and then click the average nearest neighbor. Okay, so if we go to the toolbox, which is in analysis, then once we get there we can go into the toolbox session and we can find spatial statistics tools, and we can look at analyzing patterns, and we can find the average nearest neighbor. Okay, so it took a couple of seconds to load on my machine when I looked at this previously, but you can, when it opens, place the nests into the input factor. We're going to use the Euclidean distance method as the way that we're going to measure distance here. So this is just the straight line distance, and that's for area. Let's put in, I think I'd used 600,000. Okay, so So this is actually currently in US feet. I don't normally use imperial projections, but this is what the data was in. Okay, so I thought I'd provide that case for you. And basically, once we've got that, so we've been through the geoprocessing here, and I've opened the results, we're then able to actually look at, let me open this simultaneously, the NN observed. Okay, so that's the NND, and that's, if you look down here, we've got the observed mean distance, which is 9.46. Here we go, we've got that number here. And then we've got the NN expected value, which is 21.92645 here. And then you remember in the class that actually this gives us the test statistic, but we can actually get the standardized index here, this R value, by dividing the NND bar by the NND R bar value that we get. Okay, and that's going to give us a relative indicator of how clustered or dispersed these data are. Okay. And essentially what we end up with is a z-score which is minus 19.2, so it's very large, and we get a p-value of 0, which means it's obviously very, very highly significant. So it's well below that 0.05 level that we'd be looking at if we wanted to be at least 95% certain that the results haven't just completely occurred by chance. And as a consequence of that, we would reject the null hypothesis and basically we would retain we would reject the null hypothesis, and we would accept the alternative hypothesis that basically the placement of these nests is not random. Okay, and obviously they appeared highly clustered when we actually look at that, when we actually looked at those data points, but we didn't test whether these data points were clustered, which obviously would be a one-tailed test. We just said, are they significantly different? And the answer was yes, they are. They're significantly different from random. Here they are actually clustered. Okay, so that nearest neighbor index that we got before was 0.43, so that's the ratio. So this is basically saying that they're quite clustered, and they are significantly clustered as well. So that's basically how you run this average nearest neighbor test. Okay. So that's the first test. You'll be glad to know that we're only going to go on to one more example now, so it's fairly short, this practical session today. So you can either get rid of this, as I'm going to do here, or you can just start a new map, whatever you prefer. And basically now what I'm going to do is I'm going to go back to our data, and we're going to get the low 48 county shapefile, and we're just going to drag that shapefile and drop it into the actual working map. And here we go, we actually have those county level shapes for all of the United States, and we actually have quite a bit of data associated with those county level shapefiles. Okay, and we're going to explore Moran's eye. So you remember that we covered this within the session, and Moran's index, here we go, helps us to identify a non-random spatial pattern, so we can look for things like spatial autocorrelation, and we can produce the Moran's eye index like this. So thankfully for you, I'm not going to make you calculate it. You're going to be able to use it within ArcGIS. But essentially, if I is below 0, then these are dispersed metrics that we've got. If I is above 0, then it's basically clustered data that we've got, and if I is equal to 0, then we've got randomly distributed data. Okay. So what I'd like us to do is to go to Symbology first, so we can go low county, we can right-click, go to Symbology. Here we can click graduated colors, and we can start to look at some of those metrics that we've got. So if we go to the field level, we've got the population for the year 2000. We've got the population for the year 2001 as well. Sorry, I think that this is, okay, let me just change this metric. So basically what we've got is a whole load of demographic information. Okay, so we've got the number of males here, obviously quite evenly distributed, maybe higher in some areas, like particularly the urban areas. And then we have ages, so we've got data on different age ranges. And then we've also got things like, we've got racial information, okay, so we've got genders here, we've got ages, demographic information, and we've got information on things like the race of people living in different areas, okay. So what can we do with this data? So let's start to have a look first at the proportion of, I think it's the number of Hispanic people living in each area, okay? Because obviously we kind of a priori know that this is probably going to be quite a clustered metric. We know that it's probably not going to be spread evenly, and there's going to be certain processes that basically have been leading to that clustering of certain races of people in certain places. So this is quite an interesting one for us to be able to actually study. So here we've got this Hispanic rate. We're going to normalize against the population in the year 2000. Okay. So basically what this is saying is this is the number of people from the census that's recorded who are Hispanic relative to the proportion in the year 2000. So basically over the last 20 years, because the border wall is quite porous, there's been a lot of migration, migratory trends towards the southern parts of the United States. And that's quite visible here with the proportion of Hispanic people living in these areas relative to the number of people recorded in the year 2000. Okay, so we can quite visibly see that. So my question to you obviously is going to be whether you think that these data points are clustered together, dispersed, or just randomly spread. Okay, and I suspect what you're probably going to say is that they seem to be quite clustered. In fact, not only are they quite clustered, they're quite clustered with the gradient basically spanning along that land border, which crosses into Mexico. Okay, so what can we do with these? What can we do with these tools? So essentially, we can also look at how that rates for males against the year population 2000. So now let's do that and see what map we get. And kind of in contrast to that really quite kind of clustered view that we had across space, where the previous rate was very much against the land border with the neighboring country Mexico. Here we have the proportion of males, which obviously it seems to be kind of a lot more random. Okay, so it doesn't seem that there's any kind of underlying kind of process or kind of outcome related to the spatial distribution of this metric, right? So that's quite interesting. So we've got these two kind of contrasting metrics. So what are we going to do? So look, we can basically go into the ARC toolbox, go into the spatial statistics tools. We can analyze patterns, and we can look at the level of spatial autocorrelation that we have within these data sets. Okay, so let's go to the spatial statistics toolbox. Tools, spatial statistics, spatial autocorrelation, down here. And we can place the low 48 county into the input feature. And then once we get to the field value here, what I'd like you to do is to pick the Hispanic rate. So this is basically the rate relative to the year 2000. And then we can basically use contiguity edges only, and we can run a report for that, okay? So that's just running in the background now. I'm just going to change this to the Hispanic rate. So this is basically what we're assessing, okay? And it's looking at the Moran's I for this particular data rate that we've got. Now obviously it's taking a bit longer than the previous cases, but that's because here we've got counties, right? So this is going to be, I mean, it must be over 1,000, I expect, of data points that's in here. Okay, it's finished now. So look, now we're able to go in and we're actually able to look at the z-score which we've got, which is very large. Okay, so it's 74. What our index, which is indicative of how clustered or unclustered the data are. Okay, this is our I metric, so Moran's I. So obviously this is close to 1, okay, so this is indicating very, very high level of clustering. And actually the p-value that we get for this is below 0.001, okay, so it's highly, highly significant. So we have very strong clustering here for the Hispanic rate relative to the kind of year 2000 population, okay. So that's really interesting. So we can do the same with inverse distance weighting too. So this is just slightly changing how we basically do this estimation, right? Okay, so I'm just running that now. We've got details. And again, we get it slightly less clustered. This time we get 0.78, but we've still got, we've got an even larger z-score, and it's highly significant as well. So it's significant for both of these cases, regardless of the distance, sorry, the spatial relationship conceptualization that we use. So look, let's now play with the male rate, okay? So before we were focusing just on the Hispanic rate, which we knew kind of in advance was highly spatially clustered. Let's look at the male rate. Let's go to contiguity edges. Inverse distance weighting, sorry. Here we go, inverse distance weighting. We're going to use a band of 200k. This unfortunately isn't in feet. So let's just do meters. There we go, we're in meters there. And I want to use 200,000, okay. So let's run this now. What do we get? So look at the details. Now for the male rate, that's really interesting. We do have a p-value which is highly significant. And what this is saying is sorry, let's first interpret the index, okay? So what this is saying is 0.11, so it's slightly positively autocorrelated, which is interesting, but we don't actually have that much of a strong effect relative to what we saw before, but the result is still significant, which means that there is a very, very slight degree of clustering, which is quite interesting. So let's look now at what we can do with the other runs that we can look at. So if we go to actually mapping these clusters, we can cluster and use some outlier analysis to look at which category each of those areas kind of falls into. Okay, so let's go back to our geoprocessing toolbox. So now we're here, we're going to mapping clusters, cluster and outlier analysis. Let's put in the Hispanic rate again, which is what we've got here, inverse distance weighting, and use 200,000. Okay, so inverse distance weighting, and then for the distance band for the threshold, put in 200,000 meters, so it's 200 kilometers. And we've got our processing taking place right now. Fantastic. So for that Hispanic rate that we looked at, what this is basically saying, and I'll just remind you before we get to that interpretation, is that we can actually look at where these points are within this, this quadrant here, these sets of quadrants. So from Moran's eye, basically we have those areas where we have positive correlation and quite a bit of clustering, and we also have the low correlation, okay, and below average clustering as well. So we can disaggregate these in this way, and then we have these outliers here. So remember that we looked at it in the actual lecture for Detroit in terms of racial composition. But then we can look at it also here for the Hispanic rate. Okay, so we have these border areas here which are significant and which are highly clustered and have above average rates of Hispanic people living in those counties. And then we have these blue areas here which are also highly significant but have the opposite. They have low numbers of Hispanic people living with them. Within them, and then obviously we have the kind of outlier areas. Okay, so those outlier areas are any of those red or blue areas that basically have something else going on within them, okay? But what's interesting is we have those very high levels of Hispanic people within the border areas. That's obvious on the border with Mexico, but then we've also obviously got a cluster in Florida with proximity to places like in the Caribbean, like Cuba, and then also obviously within the kind of New York city region, essentially, so including Long Island as well. So that kind of logically makes sense to us, right? Because we know that these are areas where you have kind of above average rates of Hispanic people clustering. Partially also because they're cities, but also because of historical reasons, okay? So that was quite interesting. Now let's look at the male rate, okay? So what we need to do is go back to these clustering and outlier analysis metrics, click the male rate, and we're going to keep that that size that we've got there, the 200,000 meter threshold. Just remember what coordinate reference system you're in, because basically down here it was in feet when I first loaded it in. If you're going to use 200,000 as I'm doing here, it needs to be in meters. So you either need to convert this coordinate reference system into meters, into metric, or you need to convert the distance band into imperial if you want to keep it in feet. Okay, so this is basically what we get for the male rate relative to the year 2000. So all of these white areas are basically non-significant. What's interesting is those areas where we've got the red. So this is where, the pinkish colour, this is where we've got above average number of males relative to the year 2000. And also they're significant and clustered, okay? And then the blue is where we've got below average number of males relative to the year 2000, and they're significant there as well. And then obviously this darker blue and the red is where we've got outliers, which are significant, okay? Great, well, I'm not going to keep you much longer than that. You've now got the instructions for carrying out these analysis. You've got the homework, the assignment that's been set, and hopefully you'll enjoy the fact that it's been relatively easy and short this week. Do reach out to me if you've got any questions. I'm sure those of you who don't appreciate doing lots of R coding will enjoy the fact that this week we won't be doing that type of hard work. But don't hesitate to reach out to me if you've got any questions, and if I don't hear from you, then I'll look forward to hearing from you at some point in the future, hopefully when you manage to pick up my emails, which I've now sent to all of you basically just to catch up, because we're moving into that final third of the semester, and I've had all of your results from your midterms, and you all did very well. I'm glad, and it looks like many of you are going to go on and do great things when you finish this course. So well done to you. Just make sure you kind of keep up the hard work over the next couple of weeks so that you can finish on a real high. Thanks for tuning in, and I'll see you again next time. Goodbye.